Welcome to the fourth objective of our day 15, day 16 note-taking guide, which will take us to the end of chapter 17. In this objective, what we're going to talk about are the nuts and bolts of translation. We're going to mainly focus on the different stages of translation and cover some specific properties of translation as we go through this. So let's go ahead and get started. Okay, let's go and get started. As we've done with most of the chapters, the objectives, let's start with the central dogma piece of DNA, the gene, and we converted that to a messenger RNA. And then through the process of transcription, and we'll abbreviate that here with TXN, and then we modified it and got our modified messenger RNA with the 5' G cap and then the poly A tail, if you remember, at the 3' end. So let's put 5' and 3'. Now what we're going to do is we're going to take this messenger RNA, and today what we're going to talk about in this objective is how it's translated. And we're going to see as it's translated that we make our primary amino acid structure with the amino group on the far left ending with a carboxyl group. And then this will eventually become fully processed and folded into more of a globular structure that's been modified. Okay, so on this arrow, let's put modified. So we're going to focus on translation mainly today with this objective and just a tiny bit on modification of that protein. As we go through translation, there are going to be 3 events we talk about, similar to as we saw with transcription. So we're going to have initiation, elongation, and then finally termination. In going through these 3 events, let's go ahead on the next slide. We'll write out the messenger RNA and then how the ribosomes bind to it and how we start making a protein. So let's go ahead and go to a new page. Okay, so let's go ahead and look at translation, beginning with initiation. And so let's begin by drawing our messenger RNA with our 5' G cap here and our poly A tail. And remember, this is our messenger RNA. So I'm going to write mRNA underneath it just to remind us that this is our messenger RNA. And that's our 3' end. Now, in order for the initiation to occur, 3 things are needed. The first thing is this messenger RNA, our ribosomes. And the third thing we're going to need is tRNA. And let's go ahead and draw some amino acids here. I'm sorry, codons. And remember, this whole red line here is a string of nucleotides. And so our first codon here is going to be AUG. And we can make up the next ones. Let's make up GGG, UUU. All right, so let's go ahead and have our ribosome bind. And there's 2 subunits of the ribosome. The first one we're going to put here. And the next one I'm going to draw up here. And it's a little bit bigger, like so. Then I need to bring in our tRNA that's going to recognize this AUG. And a tRNA, I'm going to draw what a tRNA really looks like, and then I'm going to draw a more simplified one in our drawing. But a tRNA looks something like this. It's going to bind over here to the 5' end of this messenger RNA, and this being an RNA molecule, it still has to follow the same rules of antiparallel and complementarity. So we have our 3' end here, and our 5' end here. This region right down here at the very bottom of the loop here, we call the anticodon. I'm going to spell that out for you, anticodon. And it will have complementarity with the AUG in this case. And so that's got to be AUAC. So these bases, UAC, or nucleotides, UAC, are right here at the bottom here. This will bind to the AUG, just like so. I'm going to draw it just as kind of a plus sign here, or a T sign. And every tRNA that is UAC at the bottom here will always have the amino acid methionine attached to it, just like here, attached to this 3' N. That's how we know that a methionine will always be added here. It's because the tRNA with this very specific anticodon that will bind to this specific codon brings it in. And so for simplicity, I'm just going to draw methionine right here. I'm going to use the single letter abbreviation M. So that's methionine. And this is initiation. We've just accomplished initiation. So let's write initiation here, so we know what we just did. Now the next step of elongation will require 3 events to occur. So before we get there, let's redraw this here, right down here. 5' G right here. And we have our messenger RNA coming across here with our poly A tail. And we still have our our codons here, AUG, GGG is our next codon. And remember, after AUG, it doesn't matter which codon comes next. It has to start with AUG, but the rest can vary. I'm picking these because there's relatively few codons that I have memorized, and these happen to be 2 of them. All right, so now let's draw our ribosome back on here. And our tRNA. So we still have our initiating tRNA here with methionine attached to it. All right, now we're ready to plop on our next amino acid. And we call this step codon recognition. So let's go ahead and write that here. Codon recognition. And what we mean by that is we'll have this tRNA that's, remember, it's hard to visualize this here, but this is occurring in the cytoplasm. All along this area here, it's just flooded with tRNAs, a whole wide variety of them, all with a different anticodon on it, with a different amino acid that is representative of that anticodon. So this next one's going to come in right here, and it's going to bind to this GGG, so we know that the anticodon has to be CCC. So that's codon recognition. It comes in here. And attached to this one is glycine. And the single letter code for glycine is G. And so the second step of elongation is forming that peptide bond. And so the methionine and the glycine will form a peptide bond. Now, the last step here is called translocation. And to show that, we're going to have to draw this one more time. 5' G cap. And let's go ahead and put our codons back here. And of course we have to draw our ribosome. And part of translocation, well, what translocation means is that messenger RNA is fed through the ribosome. So now we're going to have a shift. This ribosome now moves to the next codon, just like so. And so now sitting at this GGG codon, we have this tRNA that has the CCC attached. I'm not going to redraw it, but the anticodon is still CCC, and it's still bound to this GGG. And attached to this now is glycine and methionine. It's the growing peptide chain. And you know what? We should go ahead and just indicate that this is the N-terminus. The first thing that pops off here is the N-terminus. So at the N-terminal end, we have a methionine and glycine. And with this translocation, I should have written translocation here. So with the completion of translocation, we've completed our first round of elongation. And so this is elongation. And now the next round of elongation will occur, where the next tRNA will come along and recognize the UUU codon. Okay, so here comes this tRNA. It looks very similar to the previous ones, except it has the anticodon of AAA on it. I didn't really leave any room to write it here, but the anticodon will be AAA. Attached to this tRNA that has an AAA as an anticodon will be the amino acid phenylalanine. And the one-letter code for phenylalanine is F. Then a peptide bond will form between this phenylalanine and this glycine for the second step of peptide bond formation. And then once again, this ribosome will move along in this direction. And this will continue this elongation process until we get to the very end here. And what happens in this at the very end here? Well, let's go ahead and write a stop codon here. There are 3 stop codons. One of my favorites is UGA. So let's just write UGA. And let's go ahead and give ourselves another codon right here, GUG. All right, so remember this ribosome is moving all along here until it gets to this spot right here. All right, so our ribosome binds here and here. I'm going to have to go up into these letters here. I apologize for that. It makes it look a little sloppy. And we have our tRNA here in this at the GUG site. All right, so I'm going to draw the tRNA a little smaller. Attached to this tRNA, I'm going to draw it over here. Attached to this tRNA, we're still going to have our growing peptide protein sequence here. So right attached to this is going to be the one that's GUG, and that turns out to be serine. Oh, I'm sorry, not serine, valine. So it's a V. And then we have all of these other amino acids that were coded for by all of these codons that we didn't decipher right now. So we're going to have this string of amino acids here, followed by still connecting to glycine and methionine. And again, remember this is the N-terminus N. The amino groups go here. Okay, and valine here is this N. And well, we'll stop. We won't mention that quite yet. Now, how does it know to stop? Remember, we said there's no tRNA that's going to pop in here and recognize UGA. There's no amino acid that is a stop. What happens is there's this large protein that we call a release factor. This release factor, it's kind of like this big bully protein. It'll plop right in here and block this UGA site. This causes the translocation machinery to pause, and that pause is enough to release the ribosome from here and release the messenger RNA, and finally to release the protein. Okay, and remember we have our protein. Let's just redraw it here. As it's just been released from the ribosome, we have our N-terminus N here, followed by a methionine, a glycine, and this whole string of other proteins, I mean amino acids, ending with valine, and then our carboxy N. Let me make the amino N look more official as well by adding the hydrogens to it. Okay, so that's our protein that's just been released. So these are our 3 steps: initiation, elongation, and then termination. And I should go ahead and write the word termination right here, because that was our last step. We've just released this protein, and now what happens next? What happens next is, well, let's go to the next slide real quick. This part won't take too long. So let's go ahead and draw our kind of a simple schematic of our protein. We have our N-terminus, and then we have our primary structure, followed by our C-terminus. So we have our methionine, phenylalanine, and then a whole bunch of amino acids followed by valine at the end. What has to happen next is and let's review some terms here. Remember, this is our primary structure of the protein. It goes through a secondary folding and then finally tertiary folding to end up with a fully folded protein that usually forms these nice globular structures. We still have our N-terminus here and our C-terminus here. It's just that it's nicely folded. And remember, the protein that assists in this is called the chaperonin. Now, often this is all that's necessary. We have a nice fully functional protein. But sometimes we have to go through a process called post-translational modification. So let's go ahead and write that long word here. Post-translation modification. And what does this mean? Well, different chemicals now can be added to the protein to give it its fully functional state. Some of these chemicals that can be added to it might be a methyl group. It could be a phosphate group. It could be an acetyl group that's added to the protein. These are all, you don't need to worry about the names of the chemicals here or the chemical structures, but these are all small chemicals. We may even have, well, let's just stick with these three here. What these will do, they can alter the way that this protein is folded or alter the way that this protein is charged. All of these can and do affect the activity of this protein. Now, what we're going to talk about with the next podcast is how we can change this protein by mutating the DNA. And we talked about that in one of our activities in class. You know, if you mutate that DNA, we can get a completely different protein here. And we'll talk more about that in the next podcast. Now, before we end here, I want to show you the last part of that Bioflix video that's on mastering to help kind of tie this all together. So here's our messenger RNA. Here's are the tRNAs floating around, and here's our ribosome that's going to bind with the correct initiating tRNA that carries methionine. And the large subunit is now going to fall down on top of it, and now it's ready for elongation. The next amino acid, tRNA comes in with its accompanying amino acid. The amino acids are connected to each other. This tRNA is now removed, and this shifts down. Now the next tRNA with the appropriate amino acid is going to be added. They're going to shift here by forming a bond between the growing amino acid chain. tRNA is lost. The next one comes in. Here's just showing you where the anticodon is of the tRNA and then the codon of the messenger RNA. And so that's how it specifies which amino acid to bring into the growing chain. It doesn't show it, but at some point it hits that stop codon and it falls apart. All right, let's go ahead and stop here. If you have any questions, make sure you come see me. If not, I'll see you in class. Have a good one. Bye.